So welcome to the session where we are discussing the subject solid mechanics. So in previous lecture we have discussed about the tensor, and so far we are discussing the tensor. We have defined scalar, vector, and what is scalar and what is vector, and what are the difference between scalar and vector. So basically the scalar is a tensor of order 0. That means it will have only magnitude, it will have no direction. That means it will have 0 basis vector. Yeah, so that's why it is a tensor of 0 order. And we have seen the vector is a tensor of order 1. That means for a vector it will have 3 components, and to define each and every components you need one basis vector. So that means one basis vector, that means you need one directions to define each component. So that's why it is a order of 1, it's a tensor of order 1. So today we will basically start with new topic, that is the second order tensor. So second order tensor is a linear transformation which transforms a vector or vector space to another vector or vector space. You will see in the example, that is Ax equal to b, where A is a second order tensor and x and b are the two vectors. So basically the second order tensor transforms a vector into another vector. Now the vector represents tensor representation. The tensor is represented by a capital letters or symbols. Like symbols means if you write A like this, and if you like a double bar on this A, so it is the representation of tensor. Clear? It is the representation of tensor. So represented by a capital, bold letters and symbols. Okay. Now the second order tensor have two directions, one magnitude. That means you need two basis vector to define a component of a tensor. So for a second order tensor, n equal to 2, and for three-dimensional space, n equal to 3, m to the power n equal to 3 to the power 2, that is 3 square, it is equal to 9. So that means a second order tensor have 9 components. Clear? Examples is the stress tensor. So that is, in the subsequent lecture we will discuss about the stress tensor in details, but at this moment you just need to understood that this is the stress tensor. Example of second order tensor, the stress tensor. The sigma ij, it is represented in matrix form. Okay, so sigma ij, and it will have 9 components. You can see it will have 9 components, that is sigma xx, sigma xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, and sigma zz. So the stress will have two directions. That means one represents the plane, that means the direction of normal to the plane, and one is the direction of the stress, in which directions the stress is acting. So these are the 9 components. So this one is the example of stress tensor. Now another example is your strain tensor, and it will have also 9 components, and subsequent lecture you will see the strain tensor in details. Now another example is the identity tensor. Identity tensor, you know, it is a matrix representation. the off diagonal elements are 0 and the diagonal elements are 1. So it is also second order tensor. Okay, so move to the next. So now we will introduce the index notation, which is very important for understanding the subject solid mechanics. There are lots of equations where we will use different initial notation, which basically reduces the representation. Okay, so let us an example. A vector can be represented by in small letter v and it is in bold. So v1 e1 plus v2 e2 plus v3 e3, where e1 e2 and e3 are the basis vector. So for three-dimensional case, if you take an example, so x1 y1 x y z, so instead of x y z I am basically using e1 e2 and e3. so e1 is the unit vector along x-axis and e2 is the unit vector along y-axis and e3 is the unit vector along z-axis. So rather using x y z, you basically use x1 y1 and x1 x2 and x3. Okay, now this can be represented by in summation form, that is the summation over I equal to 1 to 3, that means I varies from 1 to 3, ui ei. So that is it is summed over I. So we can remove the summation symbol and simply write v equal to vi ei, and this representation is basically the Einstein notation. So v equal to vi ei. Sometimes it is called Einstein notation or Einstein representation, where I equal to 1 to 3. Now example sorry, so VII, that means V11 plus V22 plus V33, where I varies from 1 to 3. Now we will introduce dummy and free index. So an index which does not appear in equation after summation is carried out is known as dummy index, and dummy index cannot be repeated more than twice. So you need to keep in mind this thing, the dummy index cannot be repeated more than twice. And free index is a genetic index and can have any initial form. Examples are aij xi. A dummy index is I and free index is j. So dummy index can be repeated 2 times, but it cannot be repeated more than 2 times. Where you can see the I is in a single term. In a single term, that is I is repeated twice. So that's why I is a dummy index and j is the free index. Okay. Now we'll continue the index notation. So these are the examples where that is yi equal to, that is aij xj, that is for j equal to 1, j equal to 2 and j equal to 3, we can write ai1 x1 plus ai2 x2 plus ai3 x3 for j equal to 1 to 3. Similarly, if you write for I equal to 1 2 3, so that is y1 y2 y3 can be written like this. The next is the vector and matrix representation. So vector can be represented by a column matrix. So that means the vector ai, that means the vector a can be represented by a column. So that is the a1 a2 a3, and the matrix, the component of a matrix can be represented by like this, that is aij. In initial notation aij, but in matrix it is a11 a12 a13 a21 a22 a23. So that means I and j varies from 1 to 3. So vector and matrix addition, so ai plus bi, that means you have the 2 vectors. So if you summed up 2 vectors, so the components are summed, that means a1 plus b1 plus a2 plus b2 plus a3 plus b3. Similarly, you can add 2 matrix also, aij plus bij. So aij, that means it is one matrix and Bij is another matrix, and if you add, so these are the component wise addition, A11 plus B11, A12 plus B12, like this. So we'll continue in the index notation. Now we'll see the next operation, that is the scalar multiplication. You know, if you multiply a scalar with a vector, then it is simply multiplied with all the components of a vector, like this, that is ka1, ka2, ka3. Similarly, if you multiplied a scalar with a matrix, then all the components of this matrix will be multiplied by the lambda, like this. Now you know the inner product. Inner product means the dot product. That means product of two vectors with same index represented by dot product, that is A dot B. So AI BI, same index means when you want to perform dot product, that means the index will be same. That means AI BI, that is A1 B1 plus A2 B2 plus A3 B3. You know that the dot product. Suppose you have a vector A and vector V. So in Cartesian coordinate system, E1 is the unit vector along this axis, and E2 is the unit vector along this axis. Okay, and E3 is the unit vector along this axis. Clear? So these are the three unit vectors. So this is the vector A, and this is another vector B. So A and B are the two vectors. So if you perform the dot product, then this is the dot product. Okay, where A and B are the two vectors. Now another important operation, that is the outer product, which is also known as the tensor product, and it is symbolically or in initial form it is denoted by like this, that is A tensor product B, and it is simply AI Bj, AI Bj, where I and j are varies from 1 to 3, I equal to 1 to 3, j equal to 1 to 3. So this is also known as the tensor product or dyadic product, and this Aij can be written in the matrix form, that is Aij component of this Aij, that means the component of this tensor product. So this tensor product is basically increase the dimension. The tensor product of two vectors gives a second order tensor, that means it will have 9 components, that is A1 B1, A1 B2, A1 B3, A2 B1, A2 B2, A2 B3, A3 B1, and so on. So these are the 9 components, and it is a second order tensor. So that means you have the two vector A and B, and if you make the outer product or tensor product, it will have the second order tensor. Okay, now this is the important initial notation, that is the delta Ij, which is known as the Kronecker delta symbol, Kronecker delta symbol, and this symbol is defined as delta Ij. It is equal to 0 when I not equal to j, and equal to 1 when I equal to j. So that means, so the delta Ij, so all the off diagonal elements are 0. So these diagonal elements are only 1, or it is delta 1 1, delta 2 2, delta 3 3. Now this delta Ij have some property. So delta Ij equal to delta Gi. It can be written as like this. You can, with the pen and paper, you can prove this. So delta Ii, that means the delta 1 plus delta 2 and delta 3 equal to 3. Okay, and these are the property you need to keep in mind. This on the property. Now what is the use of this Kronecker delta symbol? Now let us consider an example. You have the two vectors A, another vector B, like this, and we can write A dot B in terms of delta Ij. That means summed over I and j is the double summation summed over I and summed over j, delta ij ai bj. And so let us consider first the summation over I equal to 1, 2, 3. Then summed over j, that is delta 1j a1 bj plus summed over j delta 2j I equal to 2 a2 bj plus summed over j delta 3, that means I equal to 3 a3. And if you put all the values of j, then for delta 1 1, that means when j equal to 1, then it will gives a1 b1. When j equal to 2, then it is a2 b2, because all other terms are 0. J equal to 1 and j equal to 3, all other terms are 0. So these are the three terms, and so this is simply can be written as delta ij ai bj. Okay, so this is important notation which is known as the Kronecker delta. It is extensively used in solid mechanics. So we will see all other applications in subsequent lectures. Now here note, the Kronecker delta allows one to write the expression defining the orthogonal basis vector like e1, e2 and 3 in compact form, like that is delta ij equal to ei dot ej. Clear? So this is another property. Okay, today up to this, and in the next class we will continue with index notation. You have some other index notation. Okay, thank you.